We're going to see an example of a combustion reaction where we calculate either the heat released by the reaction, or we can calculate also the adiabatic flame temperature. We choose a new case, we add the component. The components are methane, oxygen, nitrogen, CO2, and water. Next, we choose the fluid package. We're going to choose an equation of state, so we click here on equation of state, and we choose the Pine-Robinson equation of state. We have now 5 components, which are water, oxygen, nitrogen, methane, and CO2. And we have a fluid package, the Pine-Robinson equation of state. We're going to select now the reaction tab. We're going to go to reaction and add a reaction. We're going to choose a conversion reaction. We're going to add the reaction. We're going to select the components: methane, oxygen, CO2, and water. We're going to choose the stoichiometric coefficients, which are -1, -2, 1, and 2. So now the balance error shows 0, which means that the stoichiometric coefficients are correct. The reaction is methane plus oxygen. 2 oxygen gives CO2 plus 2 H2O. Okay, it's a combustion reaction of methane in presence of oxygen. Now we go to bases. The base component is methane. The reaction phase is overall, and the conversion is 100%. I'm assuming 100% conversion. Now we're going to go to reaction set, and we're going to add to the fluid package this reaction. So we choose add set to fluid package. That's it. We can now enter the simulation environment. We choose a feed stream. I'm going to call it feed. The feed stream temperature is 25 degrees Celsius. The pressure is 101.325 kilopascal. The molar flow rate, I'm going to choose mole flow rates for each component. Okay, so CO2 is 0, and water is 0 because these are products, and methane is 100, oxygen is 300, and nitrogen is 500. I'm gonna click on OK, and now this stream is well defined. You see it's blue, dark blue. We're gonna choose a reactor, a conversion reactor. We're going to click on it and bring it here, click and drag on it. We're going to choose a feed stream as feed, a vapor stream V, and a liquid stream L. We need to specify a vapor stream and a liquid stream, even though our product is a vapor product and there will be no liquid flow rate. The flow rate of the liquid will be 0. Require a reaction set. HYSYS demand us to enter a reaction set. We go to reaction and we choose a reaction set. So now this is okay. The energy stream, we choose an energy stream E, and it tells us that we have unknown duty. So we go to worksheet and we specify an exit temperature of 200 degrees Celsius. Now the reactor has converged. As you see, everything is converged, and we can look at the reactor parameters, and we see here the heat that is released in kilojoule per hour or kilojoule per second, or kilocal per hour, or BTU per hour. This is the heat that is released by this exothermic reaction in order to have a product that has a temperature of 100 degrees Celsius, 200 degrees Celsius. We see here the stream composition of the product gas. There is no methane left because all the methane has reacted with oxygen. We use an excess oxygen, so there is some oxygen that is left, nitrogen and CO2 and water. The liquid stream has a flow rate equal 0, as you can see. The flow rate of the liquid stream is 0 because there is no liquid stream going out of the reactor. There is only a vapor stream going out of the reactor. We can calculate the adiabatic flame temperature. In order to do so, we go back to our worksheet and we delete the temperature here. And so it says unknown duty. So we have to go to design parameters and specify the duty as 0 because we are requiring an adiabatic reactor. And now it has converged. And if we go to worksheet, we find that there is the adiabatic flame temperature is 2242 degrees Celsius.